fast time scales in the system, and as you take these moments, take into consideration these time scale hierarchies here, you will get this equation with this closure. There are additional terms that have been ordered out because of this ordering. There are things like finite logarithm radius effect. So if the logarithm scale of the orbit is comparable to the fluctuations that you're interested in, there will be an additional term in this pressure tensor called gyroviscosity. So only this piece right here is the leading order contribution to the pressure stress in this ordering. If you start to relax some of these orderings, there's this additional term that you add on. Some of those have heat fluxes, whether that drops. So this becomes important in what's called a low Mach ordering. So if the Mach number of the flow is very, very small, those heat fluxes enter into this equation. There's actually discussed in the notes. We can all see in the system. There's also gyroviscous stress that you can add on here. That accounts for finite logarithm radius effects. All these things are actually in Rickinski. They're in the notes. I'm just concentrating on the leading order. Okay. So physically, what is this? So we have a viscosity. What is viscosity? Viscosity is the collisional communication of momentum between two fluid elements. So why are all these D's interfering with that process? And the reason is that here's a magnetic field line with a fluid element, and another magnetic field line with a fluid element right there. So there's a bunch of particles in here, and I'm executing Larmor motion like that. And because of this ordering, this Larmor motion is confined to a very small perpendicular region. Right? So the Larmor radius is very small for the particles in this fluid element. And so it's incredibly difficult for a particle here, which comprises this fluid element, to communicate collisionally with these guys. Because in order to do that, you have to cross the field. Now, if there's another fluid element right here, and particles in it, these particles could just stream along the magnetic field. There's nothing blocking that along the magnetic field except for collisions. So what this equation says is that there is a viscosity, but that viscosity can only target motions that are along a shared magnetic field line. That's what this double dot product is. I can only relax gradients that are along the magnetic field because across the magnetic field communication is difficult, and I can only target flows that are along the magnetic field because, well, for the same reason I just said. So what this is also referred to is anisotropic, or sometimes just Rickinski. So the disc-like term, there's two gradients, there's a collision frequency, and there's a velocity, but then there's all these unit vectors that get in the way, which have to do with the restriction of the transport to be flowing along the magnetic field instead of across the magnetic field. So this is very different from NHC, right? The only anisotropy introduced into NHC is the Lorentz force. It's only in the momentum equation. But now we have a plasma where the transport is also anisotropic, so the whole thing gets nasty. I'm not going to derive it like I did here. I'm just going to write it down. The heat flux. If there's a heat flux in the system, for the same exact reason that I'm talking about here, instead of just being some conductivity or some diffusion coefficient times a gradient of T, which is what's usually at the heat equation, now there's these dBs. So what this means is that heat flows are only generated by parallel gradients of temperature, and that heat is only flowing along the magnetic field. So it's called anisotropic conduction, or Rickinski conduction, and physics is exactly the same as here, right? If you want to communicate instead of momentum, if you want to communicate heat from that field line to this field line, you're thwarted by the Larmor radii being tiny. So it's hard to collisionally communicate across field lines. So, but you can readily communicate heat along the field, and that's exactly what this does. So once again, you have this dB type of sensor that goes bounding into these gradients in the system, which are trying to be collisionally relaxed. Good. So on page 54 of the notes, I put anisotropic conduction, I put anisotropic viscosity into the NHC equations. The full set is written there, so you can check it out. I believe that in the next lecture, no, not in the next lecture, but Professor Carter at the second lecture is going to talk about the consequences of some of these things. It turns out, despite this stuff being known to the plasma community in the 60s, there's actually a lot of surprises still occurring in astrophysical plasma communities, just waking up to this kind of stuff. So it's good that you're young and learning it now, later. Okay, so in the last 15 minutes, I'm going to talk about a situation where the collisions aren't strong enough to keep you close to a Maxwellian. So in NHC, the distribution function is always Maxwellian, and this Rickinski ordering, the distribution function is close to Maxwellian. We've basically picked up the first order correction, pressure isotropy. So while we're racing, I'll just talk a bit about kinetics. So one reason that doing these kinds of fluid theories is useful is because kinetics is a very, very rich subject. Right? Everything here that we've written down is in three-dimensional. Once you go to kinetics, and you have to start worrying about the questions from a Maxwellian, which might be large. Then you have to start worrying about velocity, space pressure, and the problem becomes 60. So you've doubled the number of dimensions of the problem. There's also a bunch of kinetic physics that is not NMHD that you have to worry about. It's just a whole course on kinetic theory of plasma, which we will not cover everything. In fact, in the plasma program here, there's like 3 courses on kinetic physics, just to cover basic kinetic theory. And I've got 15 minutes. So, yeah. So the first thing is why. So all these them. So talk about this now, and there's going to be some less on my numbers. So kinetic equation. The kinetic equation is a physical description of a plasma. So you might want to ask right away, why are we looking around with NHC? Why are we going to derive, well, I'm not going to derive it here, but a physical theory for plasma? Why can't we just take a Hamiltonian, take a bunch of particles, and just evolve the particles under the action of the Hamiltonian? It's simple, right? If you were to write a computer code, write computational physics, this is like the simplest thing that you can do. Just take a Hamiltonian of all particles. The problem in this room is 10 to 20 particles. Just roughly. And if you were to store this kind of stuff in double diffusion, this is 5 times 10 to the 7 material rate of data. And that's at one moment, so that's at time. Okay, now with all this, so that's just impractical, right? There's also another reason, there's two other reasons not to do this kind of particle-by-particle approach. One is that the system is extremely sensitive to initial conditions. So if you just put one particle on these tensor planes, displace it slightly, and then hit go, you're going to get a different answer in terms of where all the particles are at some future time. So it's chaotic. So it's not reproducible, so why would you bother with this? The third thing is, why would you even bother? You're not actually interested in the position and velocity of every single particle in this room. You're interested in some sort of macroscopic description. So why do you muck around with this in the first place? And that's what underlies kinetic theory. So what you do is you come up with a probability distribution, right? So you say that at some time, in some interval of space, in some interval of velocity, I have a certain number of particles. And things are normalized such that if I integrate over that volume of velocity, I get number density. This thing is also such that if I take the first moment, I get momentum. If I take, I'll write this one because we've already done this. I get the curve. So you can extract all these sort of fluid quantities by taking moments of the probability distribution function. In fact, that's where all these equations come from. You can rigorously derive that. Some of it's done in those. So there is a semester course, more than half of which is deriving an evolution equation for f here. So I'm not going to derive that, but I'll write it down and talk about it. Certain aspects of this you'll probably encounter in kinetic behavior stackback course or in a classical mechanics course. So this is sentence right hand side for zero. It's kind of like kind of red face sort of. It's not exactly the same, but that's what the whole course is for. So this is the velocity coordinate dot against the gradient of the distribution function. This is all the accelerations in the system dot against the velocity gradient of the distribution function. So this is the full derivative of f. It's just angled out. And then this right hand side, and this is collision. This is like that because it's a functional function, but functional function. So this is when, so this thing is single Landau, and this thing is called Blasov, or Boltzmann, or something like that. That's what I'll talk about now. What this does is it provides you with a statistical description of how the particles evolve without having to follow each individual particle. So this is coupled to Maxwell's equations. And Professor Mikulski is going to talk about this, how to solve this system on a computer. Right? It's 6 days, sometimes we say 3 and 3 days, 3 space dimensions, 3 velocity space dimensions, so it could be quite expensive. On page 57 notes, I have listed, I haven't told you what this is, the properties of it, like it conserves particle number, it conserves momentum of the system, it conserves energy of the system, it has sizable space theorem, which means that your P almost increases. It's a Hawker-Planck operator, if you know what that means. Right, so then there's a bunch of physics that you pull out of this. One way out damping, which I talk about in the notes, and I refer you to some notes by Alexander Second, which I did some really good lecture notes on way out damping, phase mixing. I'm not going to talk about that here, because it's not necessary for the rest of the talks. What I'm going to talk about in the 5 minutes, yeah, is what happens if you really don't want to solve this. So you can do linear theory on here. You know, if you skip the linear theory homework, because it's just old hat to you, and you've never done linear theory, like what Maxwell said, you're not going to be doing that. It's extremely rich. There's all sorts of things, and a lot more than not just a single talk that you get a class on kinetic theory waves that you can cover. So instead, what you want to do is you want to reduce this equation somehow. You want to remove some degrees of freedom. You might want to remove some of the dimensions of the problem. You want to do whatever you can do analytically to not have to solve this thing. And in order to do so, that brings us something called asymptotic theory. And asymptotic, you find a small parameter, which is called epsilon, and you order everything relative to this parameter. Maybe the fluctuations I'm interested in divided by the Larmor frequency is small. Maybe that's true. Maybe the Larmor radius divided by the scale within L is small. Maybe the V over C is like f1 squared or something like that. Maybe I'm relativistic. Or just 0 or something like that. So what you do is you identify these small parameters in your problem, and you look at every single term in this equation. And you figure out which ones are the biggest, which ones are the second biggest, which ones are the third biggest, and if you're really ambitious, you can go to fourth order. And this is what underlies something called kinetic MHD, and something called gyrokinetics. I don't have time to derive these here, but I've given you derivation notes. So if you really want to derive kinetic MHD, it's here in about 10 or 15 pages. If you really want to know how gyrokinetics is derived, I'll give you sort of the simplest route to getting gyrokinetics in about 10 pages in the notes. And I live here, so you can ask me. I'm not going anywhere. What I will do is I'll tell you what orderings are in each of these. So both of them use this. Both of them in the simplest form use that, so it's not relativistic. The divine rank is also 0, so it's quite unusual, both of them. So kinetic MHD has rho over any scale that you're interested in, order epsilon. Gyrokinetics has something different. So that's a small difference, but it's a huge difference in terms of what's captured by the equations. So this has, the Larmor radius is not finite. So you never have any finite Larmor radius in this system of equations. Here, the Larmor radius is finite, but only with respect to one dimension. The dimension is perpendicular to the magnetic field. You can have different orderings. I mean, in both of these orderings, you order things like the plasma beta. Here, you just order 1, which means that, yeah, beta could be 1% or beta could be 100, but it's not as small as this. You can have the mean free path divided by the ratio of inches. The standard derivation of these says that's 1, which means later on you can take the mean free path to be 0 or the mean free path to be small, but you're not building in any bias into the system of equations from the outset. So all that's done here Right, so there's one last thing that I want to say, which I have two. Which comes out of these equations. And there's two instabilities. One is called Pyros, which is an alpha wave with this. So this is the magnetic tension. We talked about this in the first lecture. It's a restoring force. In this lecture, we talked about pressure and anisotropy. Now, it turns out that P parallel is bigger than these two things combined. These are restoring forces, and this is a destabilizing force. And this alpha wave goes unstable. And so you get sharp kinks in the magnetic field, which are of order of the Larmor scale. So the extremely rapidly going instability is derived in the notes, which I encourage you to take a look at. It appears in the solar wind. You can actually see it. It's a hot topic in terms of black hole accretion and what the Pyros instability does to angular momentum transport and accretion and heat transport and galaxy clusters and things like that. And then there's a several instabilities, but I'm just explaining down two of them. One's called the near instability, which is polarized like a slow mode, and it looks like this. And the idea is that there's a bunch of particles in this magnetic bubble. And when you squeeze on this magnetic field, these particles are going to be shot. Right, these are particles that are the particles that are at rest with respect to the wave. When you squeeze this field, these particles get pushed into this medial region. And if those particles are characterized by a P curve, which is bigger than a restoring magnetic pressure force, and this restoring pillar force, these field lines blow out. This is called near instability. And those particles in here, seen in the solar wind, they're very important for regulating heat transport and providing the effective collisionality and collisionless plasma. We're just now really starting to understand the effect of these guys on the transport properties of mass physical systems, so it's a bit of a hot topic. Yeah, I'm sorry. So we're going to get started now. So I'm Elliot Goddard from UC Berkeley. I'm going to give two lectures on what was originally called, I think, just plasma astrophysics, and then it became an introduction to plasma astrophysics, and then it became selected topics in plasma astrophysics. As I think all the speakers have emphasized, these are very large subjects that we're trying to cover, and so there's necessarily a set of choices that you have to make. And so really what I've ended up doing is I'm going to focus today's lecture actually on talking about winds from stars and using the physics of stellar outflows to introduce a number of key ideas that show up in many other areas of astrophysics. So these are winds driven by different physical processes, gas pressure, radiation, and then magnetic/rotational effects. These ideas come up in our understanding of outflows from galaxies, outflows from accretion disks, angular momentum transport in accretion disks. Many of the kind of key ideas in those fields actually originate in our understanding of outflows from stars. So that's a nice way to introduce you to some of the topics. And then the next lecture, which will be on Thursday, will actually be on a very different topic, which is on understanding some of the properties of linear instabilities in fluids and in dilute plasmas, what the connection is between those, why we care about linear theory when we can just simulate everything, things like that. Also, I encourage you that if you have questions, feel free to interrupt me as I go rather than wait till the end. So I did want to start just by giving you a bit of an overview of the range of astrophysical systems and techniques that you'll be hearing about kind of in the remainder of the next few weeks. So we're interested in our studies of plasma astrophysics in those systems that are primarily relativistic, either involving bulk motions that are relativistic or relativistically hot plasmas. And there's actually a range of different techniques that can be used to describe relativistic plasmas. So when the energy in the plasma greatly exceeds the energy in the electromagnetic field greatly exceeds the energy in the plasma, you can use something called force-free electrodynamics. We kind of neglect the energy in the plasma to describe the dynamics of the system. And this is used in, for instance, in studying the properties of the magnetospheres of pulsars and understanding emission from pulsars. Then there's the general relativistic extension of magnetohydrodynamics, which we'll hear more about from Sasha Tchaikovsky. There are particle and cell methods for describing individual particle motions and the actual intrinsic kinetic theory of the relativistic plasma that Anatoly Tchaikovsky will talk about. And then in some ways, the most relativistic systems of all are systems where you have to revolve in space-time as well. So collisions between neutron stars, collisions between black holes, and Luis Renner will talk about that. The other regime, where there's actually a very similar set of techniques, is where we are not worried about relativistic motion, so the non-relativistic limits. And again, really the same three sets of techniques apply there, with the exception, of course, of dynamical space-time. So there's force-free models where you collect the pressure or the forces due to the gas. This is very useful, for instance, in understanding some properties of the solar corona. Then there's kind of the bread and butter theories of MHD and kinetic theory that we've already started to hear about from Matt and Jim. And within the fluid theory, there's actually a huge range of different models that describe different plasma conditions and that apply to different astrophysical systems. So for instance, if you're interested in relatively dense systems where collisions are common, the mean-free path is short, then ideal NHD might be a reasonable first approximation for the dynamics of the system. But even in this regime, if for instance the energy in the radiation is dynamically important, as it is in massive star formation or in luminous quasars, accretion disks around black holes, then you really have to consider a two-fluid system where you have the radiation and the gas together. So that's an extension of kind of the fluid theory to include radiation dynamically self-consistently. And this is something that I'll touch on, and then Jim will talk more about next week. And then there are regimes of dense plasmas where the ionization fraction is low, so there's a lot of neutrals around, the temperature is low, hundreds of Kelvin in the interstellar medium, and where you can't assume then that everything is well coupled to the magnetic field because there's lots of neutral particles around. And there's different ways of handling that fluid limit. There's the non-ideal effects that Matt talked about, resistivity, the Hall effect, and polar diffusion, very important in star formation and planet formation. And then in addition, there's the complication that there's actually large molecules slash particles that we generically call dust grains that are dynamically quite important because they absorb a lot of the charge in the system. And so another multi-fluid plasma is where you consider the gas and the dust held consistently together. So this is all kind of within the rubric of NHC. These are the different microphysics that you have to worry about in different astrophysical systems. The other limit where we worry about deviations from ideal NHC is the one that Matt touched on today, which is the low collisionality limit, where we worry about things like atomic conduction and viscosity. More generally, we worry about the pressure being a tensor, not a scalar, and things like that. So I'll touch on this a little bit as well in the lecture next week. So this should give you a sense, really, of the large diversity of astrophysical plasma physics. Depending on the systems you're interested in studying, these different techniques will need to be brought to bear. What I'm going to focus on today, largely, is fluid models, including a little bit of effects of kinetic theory, and next time in my lecture on Thursday, I'll touch on even more some aspects of kinetic theory. Okay, so that's kind of some broader context. What I want to focus on, as I mentioned, is understanding outflows from stars really as a great astrophysical example of introducing you to a range of physical processes and a range of techniques that show up in many different areas of plasma astrophysics. And I'm going to organize this by studying basically different ways that outflows from stars are launched. One is by thermal pressure, which is kind of the underlying mechanism launching the outflow of the sun. Then there's stars that are more rapidly rotating. The dominant kind of source of energy for the outflow is actually the rotation of the star tapped by the magnetic field. This is generically known as magnetically driven outflows or magnetocentrically driven outflows to highlight the combination of rotation, magneto, and centrifugal forces rotation. And this model of outflows driven by a combination of rotation and magnetic fields is particularly important in the theory of accretion disk, and this is something you'll hear a lot more about, but the simplest context in which to understand this theory is actually just magnetized rotating stars, so we'll talk some about that. And then the last example of outflows from stars is outflows driven by radiation pressure, where it's really the momentum of the photons being transferred to the gas which drives the outflow. So you have enough momentum deposited in the gas to overcome the force of gravity, and that's what actually drives the outflow. This is generically described by the luminosity exceeding the Eddington luminosity, being the luminosity where radiation pressure and gravity balance. So if the luminosity is larger than that, you can drive an outflow. And there's different ways of doing that. There's different ways that the photons can couple to the gas efficiently to drive an outflow. And in particular, I'll mention two different mechanisms which are relevant in different types of stars. And then at the end, what I really like to stress is that all of this physics described in the context of stars actually applies to a wide range of other systems. Galactic winds, in particular, a lot of this theory is relevant to the theory of accretion disk that you'll hear a lot more about later in the next few weeks. And then some of the kinetic theory of solar wind shows up in other kinetic theory contexts as well. Okay, so that's kind of an overview of the different mechanisms that we'll be talking about. So I want to start by describing just a little bit empirically what we know of the sun. It's actually a movie of the sun in white light. You can see the kind of coronal mass projection there. This is the disk of the sun blocked out by a coronagraph. Comets do not actually generate coronal mass projections, just like what it might look like in this movie. That's just a coincidence. The outflow from the sun, in many ways, is irrelevant for the overall dynamical evolution of the sun. The outflow now from the sun does not take away very much mass. Over 10 billion years, the sun will lose 10 minus 4 solar masses by its current outflow rate, and it doesn't take away much energy. The kinetic energy in the outflow of the sun is actually negligible as an energy sink compared to photons leaving the star. What turns out to be important about the solar wind is actually that the solar wind is efficiently extracting the angular momentum of the sun. The sun was rotating 10 or 30 or 50 times faster at birth than it is today, and it has lost that angular momentum by magnetic force due to the solar wind, and that's something we'll return to. We can measure, by observations like this, the thermal properties of the corona, actually as a function of distance from the sun, to just give you a feel of the numbers. At about 2 solar radii, the density is about 1 billion particles per centimeter cubed. The magnetic field strength is about a Gauss. The temperature of the plasma is a few million degrees Kelvin. The energy is mostly in the magnetic field, not in thermal energy. The energy density in the magnetic field is 100 times or more the energy density in the gas, so this plasma beta parameter is quite small. So it's actually magnetically dominated, not a thermally dominated plasma. Moreover, we can actually measure that the solar corona, at least at this distance, is not in thermal equilibrium. The proton temperature does not equal the electron temperature. The helium temperature, the oxygen temperature, the neon temperature does not equal the proton temperature. So these are just measured quantities from spectroscopic diagnostics. It's even more complicated than that, as Matt alluded to. Temperatures don't need to be the same in different directions with respect to the magnetic field, and that's actually also a measured property of the solar wind. So this lack of thermal equilibrium is all a consequence of the fact that the mean free path of the corona is comparable to the size of the corona, so it's not a very collisional system. So what this tells you, if you kind of follow it along with Matt's reasoning, is that if we want to theoretically understand the origin of the solar wind, we should really worry about the magnetic field, because there's a lot of energy in the magnetic field, and we should consider kinetic theory, because it's a collisionless plasma. And what we're going to do is do none of those to start. Instead, we're going to treat the solar wind as a purely gas pressure, hydrodynamically driven outflow. A fluid driven by gas pressure. And that actually turns out to be a rather good description of the basic properties of the solar wind. And I'll describe as we go a little more why it is that despite the fact that the energy of the magnetic field is huge and it's relatively collisionless, fluid theory does an okay job at least at describing some of the basic properties of the solar wind. So the model of the solar wind that I'm going to first start describing to you was developed by Parker in the 1950s, and it's this idea of a thermally gas pressure driven model of the solar wind. It's a very simple model. It's a spherically symmetric, steady state model for an outflow from a star driven by gas pressure. And I want to use this model to introduce some key ideas. So map conservation. So first of all, can everybody read that? Yeah, good. Okay. So mass conservation in steady state is divergence of rho v equals 0. My rho is an actual rho, not an e, like that. So notice that. Okay. So we can integrate this in spherical coordinates. This tells us I'm going to assume there's just a radial outflow. We'll relax that assumption to take into account rotation later. For now, spherically symmetric, no rotation in the outflow. So this tells us that r squared rho, the radial velocity, is equal to a constant, and in particular, that constant is the mass outflow rate, m dot 4 pi r squared rho vr is a constant. F equals ma now. Force balance is just the Lagrangian acceleration, the co-moving acceleration, v dvdr, is minus 1 over rho dpdr minus gravity, d over r squared. And I should have mentioned, actually, the notes that I sent around are two PDFs, one of which is these slides, and the other of which is a kind of more derivation. So that's conservation of mass, conservation of momentum. The simplest model of the solar wind, which is very long in detail, is to model the thermodynamics and saying just that the temperature is equal to a constant. There actually isn't a really good motivation for doing this. Maybe thermal conduction is very important because it needs to be passing long, so you might think that sets up something like constant temperature, but really this is just an algebraic simplification that gets at a lot of the key ideas. So what does this mean? Well, it means that I can write the pressure is just nkt, or that's rho kT over the average mass of the particle, say the mass of the proton. I can write the pressure then the density times the speed of sound squared. So I can get rid of dpdr then in favor of d rho dr, and I can get rid of d rho dr using r squared rho v is equal to a constant. So that means I can substitute into the momentum equation to get a single equation for the velocity by getting rid of the pressure gradient and the density gradient. And that is some straightforward algebra that you can go through. It's done in the notes. And what you get is the following equation for the radial velocity. Okay, so this is 1 over v dvdr times this quantity d squared minus df squared is equal to this stuff on the right-hand side. So this equation is at the heart of a lot of our understanding of stellar winds. It's an equation, it's called the Wind equation, that also describes spherically symmetric accretion onto a point path, bonding accretion, same basic physics in this equation. The chief property of this equation is that if I write it in terms of the velocity gradient, dvdr, it takes the form of some numerator n divided by some denominator d, and notice that this denominator d is 0 if the radial velocity equals the speed of sound. That point at which the flow velocity equals the speed of sound is known as the sonic point. And in order for the velocity gradient dvdr to be finite at that location, I require that the numerator also equals 0. So at the sonic point, both the numerator and the denominator have to equal 0. The denominator equals 0 says the velocity is equal to the sonic point. The numerator equals 0 actually picks out a radius, and that radius, the sonic point radius, is gm divided by 2cs squared. Just by setting the right-hand side there equal to, just by setting the right-hand side of the momentum equation there equals to 0. Okay, so let me show you in a little more detail the kind of properties of the solutions to this equation. So what this plot shows, this shows velocity as a function of radius. One here is the sonic point. And we're interested in studying stellar winds. We're interested in solutions where the surface of the star is not moving out really fast. It's initially very slow deep in the star. So we're interested in solutions that start off relatively slow. And what you'll notice is that there's actually 3 classes of solutions of this differential equation that start at low velocity. One set of solutions, you go out, you accelerate, the velocity gradient becomes infinite, and then you come back in. So this is a solution where at the place where the velocity equals the speed of sound, the denominator is 0, but the numerator is finite, so dvdr diverges. This is a double-valued solution also at radius. At one radius, there's 2 possible velocities. So this is a mathematically fine solution, but a physically unphysical solution. The other class of solutions you'll notice is a set of solutions where the flow accelerates out, reaches some maximum speed, dvdr is 0 there, and then it settles back down and the velocity goes to 0. These are solutions where at the sonic point, the numerator is 0, the right-hand side is 0, but the velocity doesn't equal the sonic point, doesn't equal the sound speed at that location. So the right-hand side is 0, the left-hand side, dr is not cs, so that means dvdr is 0 at the sonic point. That's why these solutions all have 0 gradient at the sonic point. These solutions, because the flow is always subsonic, these solutions are almost equivalent to having neglected from the start this term in the momentum equation. Why? This term is of order v squared over r. This term, the pressure gradient, is of order the sound speed squared divided by r. So if the velocity is everywhere as long as the speed of sound, then I can diversify the just neglect the velocity term, and my solution for the density field is just given by hydrostatic balance. Pressure balance is gravity. The problem with those solutions is that these solutions turn out to have very large pressure at large distances from the star. And so they can't match onto a realistic ambient medium. They're overpressurized relative to their surroundings. And the fact that they're overpressurized relative to their surroundings is what drives an outflow. The pressure is very large compared to the ambient pressure of gas surrounding the sun, and that continues to push stuff out, and it accelerates the flow out along this solution, which is the solution that goes through this sonic point where the velocity equals, where I satisfy both of these boundary conditions. So the velocity equals the speed of sound and the radius equals the sonic point range. So this is the unique solution that accelerates smoothly out and matches onto a realistic ambient medium. So one of the things, so this then is kind of the solar wind solution. One of the things you'll notice about this problem, in terms of the mathematical structure of this problem, is that what I've done is I've varied something about the initial conditions here to get this infinite family of solutions. And what I'm really varying is the first order differential equation. So what I'm really varying is the initial velocity of the outflow at some arbitrarily chosen initial radius. And what happens is the requirement that the flow smoothly accelerate out through the sonic point uniquely picks out one of this infinite family of solutions. These are boundary conditions that specify the solution. And this actually specifies the mass outflow rate from the star. If you imagine I know deep in the star what the density and temperature are from a stellar model, what I've now done is uniquely determine the velocity at that point, the initial condition for this differential equation. So if I know the density and velocity, I know the mass outflow. So these boundary conditions of smoothly going through a sonic transition actually specify the mass outflow rate from a star. And that's a very important property, generically, of these outflow solutions from stars. Okay, so that's really the core physics behind thermally driven outflows, like models of the solar wind. So any questions about that before I go on? I'll talk a little bit later about kind of fancy modern versions of this theory. Okay. The problem, you might think, with this theory is that why should it apply at all to the solar wind, given that I told you that actually most of the energy is stored in the magnetic field, not in the gas. So why are we neglecting the magnetic field here if there's all this energy in the magnetic field? And secondly, why am I using a fluid theory if the system is actually relatively collisionless? And so what I want to do is talk a little bit about the theory of outflows like this first, but including the effects of the magnetic field. So, magnetic fields in stars, the kind of topology of the magnetic field is very complex. I'll draw you a schematic of what things kind of sort of look like. This is actually true in the sun. There's generally both magnetic field lines that close back on the star, and there are magnetic field lines that open up. Now, if the sun were not rotating,